Hello everybody. Today we will discuss about how an ultrasound image is formed. We will also discuss about probe orientation, along with orientation of image on the screen. So let's begin with the lecture. A pulse refers to a short burst or packet of ultrasound waves emitted by the ultrasound machine's transducer. The ultrasound machine generates these pulses and sends them out through the transducer into the body. Within the body, they interact with various tissues and organs in the body when they encounter boundaries between tissues or organs with different acoustic properties, such as different density or stiffness. Some of the ultrasound energy is reflected back to the transducer to create an ultrasound image, and some is transmitted into next medium. Now we will study what is pulse echo phenomenon. The ultrasound machine emits pulses of ultrasound waves into the body. These waves bounce off objects or structures inside the body and return as echoes to the transducer. The time it takes for the echoes to return varies, depending on the distance of the object from the probe. If the structure is close to the probe, the time for the echoes to return is relatively short. The ultrasound machine interprets this short time as an indication that the object is close to the probe. Consequently, the machine represents the image of the object near the top of the screen. Conversely, objects that are further away from the probe are displayed in the far field, closer to the bottom of the screen. The ultrasound machine emits short bursts or pulses of ultrasound waves through the transducer into the body. These ultrasound waves travel through the body, passing through different tissues and organs, and as the ultrasound waves encounter a boundary or structure, such as an organ or tissue interface, some of the waves are reflected back towards the transducer as echoes, carrying information about the structures they encountered. So time of flight is the duration it takes for an ultrasound pulse to travel from the transducer to an object or structure, and back again as an echo. The clinical significance is that by knowing the time of flight and speed of sound in tissue, the ultrasound machine can calculate the distance to the object or structure that reflected the ultrasound waves. This helps in determining the depth or position of the structure within the body. Skin lines refer to the individual lines or paths along which ultrasound waves are emitted and received by the transducer. It is important to remember that usually one pulse is required for one skin line, provided we are using a single focal zone that we will study later in lecture. But if you are using two focal zones, then two pulses are required per scan line and so forth. These lines form the basis of the ultrasound image. A complete ultrasound image is composed of numerous individual scan lines, often arranged in a fan-like or sector-shaped pattern. Each scan line represents a path along which ultrasound waves were emitted and echoes were received. The density and orientation of the scan lines contribute to the overall resolution and quality of the ultrasound image. As sound waves reaches the internal body structures, reflected waves come back to transducer surface and are processed by machine. Now, depending on the amount of amplitude the reflected sound waves carry, machine generate black, white, and gray spots to form an image. Since sound travels at a known speed, the system can interpret the time it takes for the waves to return and display the structures at precise locations on the screen. Shallow structures, which reflect the sound waves first, appear at the top of the image. Deeper structures take longer to return, so they are displayed at the bottom of the screen. So what is real-time scanning? In real-time ultrasound imaging, scan lines are rapidly generated and displayed on the ultrasound monitor. This results in a dynamic and continuous image of the internal structures. Each scan line contributes to the formation of the final image. the combined information from all scan lines. Provide a comprehensive visualization of the scanned area. Nowadays, in modern ultrasound systems, operators can often adjust the settings related to scan lines, such as depth, focus, and beam width. These adjustments allow for optimization of the image quality and visualization of specific anatomical structures.